Section. Introduction. In this paper, we delve into the issue of extractable memorization in large language models, LLMs. These models, such as Pythia and GPT-Neo, can remember and potentially reveal private information from their training data. Previous research has looked into the total amount of memorized data in these models and how to extract this data. We aim to combine these two areas of study. Extractable memorization refers to the data that can be efficiently retrieved by an adversary, as opposed to discoverable memorization, which includes all memorized data, even if it can only be accessed by using other training data as prompts. We've developed a method that allows us to detect memorization in trillions of tokens of model outputs in massive datasets. Our findings show that larger and more advanced models are more susceptible to data extraction attacks. However, when we analyzed GPT 3.5 Turbo, a model designed to act as a helpful chat assistant, it seemed to memorize almost no training data. We believe this is due to the model's alignment with RLHF, a reinforcement learning method. To bypass this alignment, we found a way to prompt GPT 3.5 Turbo to deviate from its usual chatbot-style responses and behave more like a basic language model. We then checked if the text it produced was already available somewhere on the internet by comparing it to a 9 terabyte dataset compiled from several publicly available web-scale training sets. This allowed us to recover over 10,000 examples from the model's training dataset at a cost of $200. We've taken care to responsibly disclose our findings. We've shared our results with the authors of each model we studied and disclosed a specific vulnerability in ChatGPT, GPT 3.5 Turbo, to OpenAI. We believe it's now safe to share this information publicly, and hope it will draw attention to the data security and alignment challenges of generative AI models. LLMs are trained on vast text corpora, which can consist of billions to trillions of tokens. For proprietary models like GPT-4 and PaLM-2, these training sets are kept secret to protect the company's proprietary data collection pipeline and any private or licensed training data. Neural networks, especially large ones, can memorize their training data. This can be exploited by adversaries through membership inference attacks, which determine whether an example was in the training set, and data extraction attacks, which recover full training examples. We began our study by examining data extraction attacks on open models, where both the model's parameters and original training sets are publicly available. This allowed us to accurately evaluate the performance of extraction attacks from previous research. We followed the definition of memorization given by Carlini et al., 2021, which states that a string is memorized if it can be produced verbatim by the model's generation routine. We then defined extractable memorization as a training set example that an adversary can prompt the model to produce. Previous research has faced two main challenges: designing prompts that best elicit memorization in a model, and testing whether the attack worked, i.e., whether the model's output is training data or not. We aim to answer why there is such a large observed gap between extractable and discoverable memorization in the literature. We believe that existing extraction attacks are actually a lot more successful at recovering training data than what prior work indicates. Section Summary. In this section, the authors introduce the concept of extractable memorization in language models, which refers to the data that can be efficiently recovered by an adversary. They develop a methodology to detect memorization in large-scale language models and find that larger and more capable models are more vulnerable to data extraction attacks. They also discover a prompting strategy to extract training data from the GPT 3.5 Turbo model and highlight the importance of data security and alignment challenges in generative AI models. Section. Attack Methodology. We start by examining previous data extraction attacks in a controlled environment where we can test the success of the attack. Specifically, we focus on open-source models with publicly accessible training datasets. This allows us to confirm if any output generated is indeed part of the training data. However, it's important to note that the attack itself doesn't depend on knowledge of the training set. We follow the data extraction attack method proposed by Carlini and his team. First, we download 100 million bytes of data from Wikipedia and create prompts by randomly selecting hundreds of millions of continuous 5-word blocks from this dataset. Then, we independently generate an output for each prompt and store each output. Our approach differs in how we assess the effectiveness of the attack. In the previous attack, since the training data from the language model wasn't publicly available, it was necessary to manually search the internet to determine whether any generated sequence was part of the model's training dataset. In contrast, we study fully open-source models, which allows us to directly check the model's training data to see if any generated sample is memorized. However, performing a simple training set inclusion test is extremely time-consuming, as large language models are trained on datasets with trillions of tokens and we generate billions of tokens of output from each model. To make this search efficient, we use a suffix array, a data structure that stores all suffixes of the dataset in sorted order, enabling fast string lookups. We build a suffix array over the training data and then check if the generated output is in the suffix array, which is equivalent to checking if it's in the training data. We consider an extraction successful if the model outputs text that contains a substring of at least 50 tokens that is also in the training set. We chose this value based on our estimation of token overlap between news articles written after the creation of the largest training datasets. We found no overlap longer than 25 tokens, excluding direct quotations. To be extremely conservative, we doubled this value. We applied our attack to 9 open-source models of different sizes. These models were designed to facilitate scientific research and make their entire training and pipeline and dataset available, which aids our study. We generated 1 billion tokens of output for each model and then calculated the number of memorized examples by matching against the corresponding training set. From this data, we can perform 2 different types of analysis. First, we measure the fraction of model outputs that are memorized. We observe rates between 0.1% and 1%. However, this number is difficult to interpret. A model that repeatedly emits the same memorized training sequence would appear highly non-private, even if it was revealing almost no data. Therefore, we also compute the number of unique 50 token strings that we extract, which varies between several hundred thousand and several million. This allows us to observe data extraction rates much higher than previously reported. In our explorations so far, we have used a large fixed budget of generations for our extraction attacks. However, the number of generations significantly impacts the amount of extractable memorization. Memorization grows nearly linearly even after generating several hundred billion tokens. This leads to a question that hasn't been discussed in the literature. If we could query a model infinitely, how much memorization could we extract in total? Given this is infeasible, we aim to estimate the total memorization. However, the rate of extracting memorized training data is not a good predictor of the total quantity of memorization. We observe that at smaller compute budgets, one model appears to memorize more data than a larger model. However, if we query the model more, the rate of extractable memorization in the smaller model decreases, revealing that the larger model in fact memorizes more data in total. Thus, we need to find better predictors of a model's total memorization. Section Summary. In this section, the authors describe their attack methodology for extracting data from language models. They evaluate past extraction attacks on open-source models with publicly available training datasets and verify the success of the attack by checking if the generated output is contained in the training set. They use a suffix array data structure to efficiently search for the presence of generated samples in the training data. The authors apply their attack to 9 open-source models and report the fraction of model outputs that are memorized, as well as the number of unique 50 token strings extracted, which is significantly higher than previous studies. They also discuss the challenge of estimating the total amount of memorization and the need for better predictors of total memorization. Section. Extrapolating total memorization. We're now going to explore the idea of estimating the total amount of memorizable information that a language model can hold, without having to generate billions of tokens of output. Ideally, we'd like to have a measure that doesn't require us to sample too many tokens from the model and can be used to predict larger compute budgets. To do this, we need to estimate 2 things. 1. How often the model produces something memorized, and 2. How often a memorized output is new. The first value is straightforward and can be estimated as a probability. The second value, however, depends on how many memorized strings we've already seen. Let's focus on this second value. The total amount of memorization the model will ever output as we increase the number of generations doesn't depend on the first value. We can visualize the rate of new memorization by slightly modifying a figure. Instead of changing the number of generated tokens, we calculate and change the number of memorized tokens extracted. This visualization helps us see the differences between 2 models, GPT-Neo 6b and Pythia 1.4b. The slope and curvature of the plot give us insight into the model's total memorization. Pythia-1.4 produces new memorized examples less frequently than GPT-Neo-6b, and seems to reach its limit more quickly. This suggests a limit to how much training data we can use. While the slope and curvature are only estimates, they can help us understand how to make memorization more efficient. They can also help us estimate how much memorization could be extracted even if we don't have the ability to generate hundreds of billions of tokens. Let's consider an analogy. Suppose a researcher wants to know how many fish live in a lake. They could try to count each fish individually, but this would be very time-consuming and prone to errors. Instead, they could use a technique called mark and recapture. They would catch and mark a certain number of fish, n, wait for some time, and then recapture a different number of fish, k, noting how many of them were marked, l. They could then estimate the total number of fish in the lake as the product of n and k divided by l. We tried to apply this mark and recapture technique to our analysis, replacing fish with unique memorized 50 grams extractable from the model. However, this approach significantly underestimated the amount of memorization that could be extracted. The main reason for this is that not all memorized strings are equally likely to be output. A better approach is to use the good-Turing estimator, which can predict the probability that a new sample will yield a novel string, even when the distribution of extractable strings is unknown. This method uses a smoothing procedure to reduce the variance of the predictions for rare events. We can then sample an outcome according to the probabilities produced by good-Turing and update our observed frequencies accordingly. Repeating this process gives us a Monte Carlo simulation predicting the number of unique memorized examples potentially far into the future. We found that having enough observations is crucial to produce a good extrapolation. We also observed that this approach underestimates the number of unique memorized examples by GPT-Neo-6b. We compared various other methods for estimating the total quantity of memorized training under varying assumptions in the appendix. We found that good-Turing consistently gives higher quality lower bounds than other methods. Section Summary. The section discusses the challenge of estimating the total amount of extractable memorization of a language model without generating a large number of tokens. The authors propose decomposing the problem into estimating two values: the frequency of model outputs that are memorized and the frequency of new memorized generations. They use a modified visualization to compare different models and find that the good-Turing estimator provides a reliable method for predicting the number of unique memorized examples in the future. Section. Discoverable mem versus extractable mem. We aim to explore the difference between discoverable and extractable memorization in machine learning models. Specifically, we want to answer two questions: how many data samples are memorized under both definitions? And how many samples are extractable but not discoverable, or vice versa? Previous research provided a dataset of discoverable memorizations from the pile for the GPT-Neo-6b model. We compared these with the extractable memorized examples from our earlier section. The results showed that most training data from the model is not memorized under either definition. However, 30.1% of examples are discoverably memorized and 14.5% are extractably memorized. Interestingly, despite generating several hundred billion tokens, only 35% of the discoverably memorized examples were also extractable. This is significantly larger than previously thought, but it's still not the majority of the data known to be memorized. We also found an additional 11% of memorized sequences through our extractable memorization attacks that were not discoverably memorized. We further analyzed sequences from the pile that have varying numbers of duplicates. We found that highly duplicated sequences are easier to both extract and discover. From this data, we made 4 observations. First, it's surprising that a simple attack that just samples from the model can recover a large fraction, 35%, of all known memorized training data. Second, there's room for improving current extraction attacks. Third, measuring discoverable memorization is a useful and reasonably accurate way of determining data that can actually be extracted by an adversary. And fourth, there's room to improve discoverable memorization baselines. We then shifted our focus to whether different models memorize the same training examples. Since we have multiple models trained on the same training dataset, we can test if 2 independent model training runs will memorize the same training examples. We also explored extracting data from semi-closed models, which are models that have publicly available parameters, but whose training datasets and training algorithms are not known. For these models, we needed to establish our own ground truth for verifying and quantifying extractable memorization. We did this by downloading a large corpus of internet text and using it to build an auxiliary dataset. We then checked if any potentially memorized examples exist in this auxiliary dataset. If the sequence does appear, and it has a sufficiently high entropy and length, then it's extremely unlikely that the generation appears on the internet by coincidence. We used this as a proxy for testing whether the generated sequence was in the training set with a very low false positive rate. This approach has false negatives. It will not identify all memorized generations because we do not have a complete picture of the training data. Thus, our results yield a lower bound on the amount of memorization present in the model. Section Summary. In this section, the authors investigate the gap between extractable and discoverable memorization in language models. They compare the number of samples that are extractable but not discoverable, and vice versa. They find that only 35% of the examples that are discoverably memorized are also extractable, and they uncover an additional 11% of memorized sequences through extractable memorization attacks that were not discoverably memorized. The authors also explore the memorization behavior of different models trained on the same dataset and analyze the amount of memorized data that can be extracted from semi-closed models. They propose a methodology to establish a ground truth for verifying and quantifying extractable memorization by checking if model outputs appear in a large corpus of internet text. Section. Building AUX dataset. We've put together a massive 9 terabytes text dataset, which we call a UXDATASET, by combining 4 of the largest language model pre-training datasets: the PILE, Refined Web, Red Pajama, and Dolma. These datasets are a mix of different sources, including Wikipedia, code, and generic Common Crawl. Some of the data is duplicated across the datasets, so we've done some basic deduplication and tokenization at the document level. However, due to its size, AUX dataset and its corresponding suffix array, a data structure that allows for efficient searches, can't fit into the memory of a single machine. So, we divided the data into 32 separate suffix arrays, which allows us to load each one into memory individually. This way, we can quickly compare large amounts of potential training data with AUX dataset. The whole process took 3 weeks on a high-memory machine on Google Cloud, including building the suffix array and performing all the dataset queries for our experiments. We then analyzed 9 different semi-closed models, including GPT-2, Llama, Falcon, Mistral, Opt, and GPT 3.5 Turbo Instruct. Some of these models, like Llama, Falcon, Mistral, and Opt, have accessible weights, but their training pipeline and datasets are not accessible. The GPT 3.5 Turbo Instruct model is only available through an API and its model weights are not public. Our main finding is that all models emit memorized training data, but there's a significant difference between model families. For example, the Mistral 7B and Falcon 7B models, which are similar in size and accuracy, differ in detected memorization by over 10 times. This could mean that Mistral memorizes less data than Falcon, or it could indicate a limitation in our dataset construction. However, even considering this, the rate of emitting memorized training data is still very high for these advanced models. In fact, the model that emits the most memorized data is GPT 3.5 Turbo Instruct. We also found that models trained for longer periods tend to memorize more than those trained for shorter periods. Some models, like Opt, are undertrained and perform poorly on benchmarks, but they memorize less training data. Other models, like Llama, are intentionally overtrained, which can lead to increased privacy leakage. Our second main finding is that the total extractable memorization of these models is on average 5 times higher than smaller models. We used the good Turing estimator to extrapolate the memorization rate of the models, but this estimator tends to underestimate the true total memorization, so the actual number of extractable memorizations is likely even higher. Section Summary. The authors collected a 9 terabytes dataset called AUX dataset by combining 4 large pre-training datasets. They used sharding to load the data into memory and performed efficient searches using a suffix array. The evaluation of the dataset took 3 weeks of compute time, and the results showed that all models emitted memorized training data, with the GPT 3.5 Turbo Instruct model being the worst offender. Additionally, larger models had a higher rate of extractable memorization compared to smaller models. Section. Extracting data from ChatGPT. We've discovered that advanced language models, like ChatGPT, can remember a significant amount of their training data. However, most people don't interact with these base models. Instead, they use versions of these models that have been adjusted to behave more in line with human preferences, making them suitable for tasks like acting as conversational agents. These adjusted models, such as the GPT 3.5 Turbo version of ChatGPT, present new challenges when trying to extract data from them. The first challenge is that these models are designed for conversation, which makes it harder to extract data using our previous method of prompting the model with random internet strings. This is because these conversationally tuned models don't allow the user to directly control the language modeling task. Instead, they expect a prompt format that indicates when it's the assistant's turn to speak. This format makes it impossible to force the model to continue any arbitrary text sequences. The second challenge is that the adjustments made to these models can cause them to avoid completing data from their training set. For example, if we asked ChatGPT to write a phrase that we know it has memorized, it might not complete the phrase. This might lead us to believe that the adjustments made to the model have successfully prevented data extraction. However, we will show that this is not the case. We first tried to adapt our previous method of using random prompts by asking the model to repeat the random tokens and continue generating. However, this method did not seem to output any training data. We ran this experiment on a large scale and found that only 0.02% of the tokens generated were part of a 50-token sequence directly copied from the training data. This is significantly less than the 0.031% and 0.85% of tokens directly copied from the training data by the smallest semi-closed model and the GPT 3.5 Turbo Instruct model, respectively. To extract data from these conversationally tuned models, we need to find a way to make the model deviate from its conversational behavior and revert to its original language modeling behavior. We found that we could do this by using a prompt that makes the model deviate from its standard conversational style. For example, if we ask the model to repeat a word indefinitely, it will initially comply but will eventually start to deviate. While the text it generates after deviating often doesn't make sense, we found that a small portion of it is directly copied from the training data. Therefore, by using this method, we can generate a large number of potential memorized examples. Section Summary. State-of-the-art language models like ChatGPT are often aligned to behave better in conversations, making them more difficult to attack using previous methods. The alignment procedure in these models, which involves using prompts and turn indicators, prevents prompt continuation attacks. However, by using a divergence attack strategy that causes the model to deviate from its alignment training, it is possible to extract data from the model, even though most of the generated text may be nonsensical. Section. Attack hyperparameters. Let's discuss the parameters of the attack we've described. We need to decide on a few things: the word the model should repeat, the command we should use to initiate the repetition, the number of times the word should be repeated, and the strategy we should use for sampling. We'll provide more details on these once we have them. Now, let's look at our main findings. By spending only 200 on queries to ChatGPT, specifically the GPT 3.5 Turbo version, we managed to extract over 10,000 unique examples of training data that the model had memorized word for word. If we had a larger budget, we believe we could extract even more data. The memorized text we extracted can be quite lengthy. The longest string we extracted was over 4,000 characters, and several hundred were over 1,000 characters. We've included a list of the 100 longest sequences we recovered in the appendix. Over 93% of the memorized strings were only produced by the model once, with the remaining strings being repeated a few times. For example, 4% of the memorized strings were produced twice, and just 0.05% of strings were produced 10 times or more. These results show that our strategy of prompting the model produces a wide variety of long, memorized outputs once the model starts to deviate. We were able to extract memorized examples from a wide range of text sources. This includes personally identifiable information, P, of dozens of individuals, various texts with adult content, literature, URLs, cryptographically random identifiers like Bitcoin addresses, code, snippets from research papers, boilerplate text that frequently appears on the internet, and instances where the model combines two memorized strings into one output. We also found that some of the model's outputs contain P. We evaluated how often this happens by labeling 15,000 generations for substrings that looked like P. We used both regular expressions to identify phone and fax numbers, email and physical addresses, and also prompted a language model to identify sensitive content within generations. We then checked whether these substrings were actual P by looking up the extracted substring in the training set. In total, 16.9% of the generations we tested contained memorized P, and 85.8% of the generations that contained potential P were actual P. Our attack involves repeating a single word many times. We found that some words are more likely to trigger memorization than others. Only words that are a single token in the vocabulary lead to memorization. Asking the model to repeat multi-token words never causes the model to emit training data because it never causes the model to deviate. When we prompt the model with single token words, we find that the effectiveness varies significantly across words. The most effective words are over 100 times more effective at recovering memorized output than the least effective words. This is due to some words not causing the model to deviate as often, and also because even if the model does deviate, some words result in less regurgitated training data. Section Summary. The attack on ChatGPT has several hyperparameters, including the word to repeat, the prefix command, the number of times to repeat the word, and the sampling strategy. By using only $200 worth of queries, the researchers were able to extract over 10,000 unique training examples from ChatGPT. The extracted text can be quite long, with some strings being over 4,000 characters. The majority of the memorized strings were omitted only once by the model, while a small percentage were repeated a few times. The attack was able to extract various types of information, including personally identifiable information, NSFW content, literature excerpts, URLs, code snippets, research paper snippets, boilerplate text, and merged memorized outputs. The researchers also evaluated the frequency of personally identifiable information in the model's outputs and found that 16.9% of the tested generations contained memorized P. Additionally, the researchers discovered that certain single token words were much more effective at eliciting memorized outputs than others, with the most effective words being over 100 times more effective than the least effective ones. Section: Quantifying total memorization. In this section, we're going to talk about how we measured the total amount of data that the AI model ChatGPT can remember. We had a budget of $200, and with that, we managed to extract over 10,000 unique examples. However, someone who is willing to spend more money could potentially extract a lot more data. We're going to discuss different ways in which our analysis might have underestimated the amount of data that ChatGPT can remember, and how we tried to estimate the true value. First, we used a method we developed earlier to estimate how much more data we could have found if we had asked ChatGPT more questions. We used a statistical tool called a good Turing estimator and found that ChatGPT could remember at least 1.5 million unique sequences of 50 tokens. However, this is likely a very rough estimate. In a previous experiment, we had to extract 500 million examples from another AI model, GPT-Neo 6b, before the good Turing estimator gave us a reliable result. We've extracted far fewer examples from ChatGPT, so we suggest not using the good Turing estimator for this data. Instead, we compared how much training data ChatGPT remembered compared to other models. We found that ChatGPT remembered unique sequences at a much higher rate than any of the other models we studied. If the trend we observed with GPT-Neo 6b holds true for ChatGPT, we estimate that ChatGPT's true memorization rate is likely in the hundreds of millions of 50-token sequences, which would be about a gigabyte of training data. We think it's likely even higher than that. As we increased the size of our auxiliary dataset, we found more data that the model had remembered. This is because a larger dataset allows us to find more overlap with the original data that ChatGPT was trained on. We also looked at how reducing the size of our dataset would have affected our results. If we had used only a 200 gigabyte subset of our dataset, we would have found slightly less than 20% of the total data that the model remembered. We found that we could predict fairly accurately how much data we would find, based on the size of our auxiliary dataset. If we used only 25% of our data, we could still predict almost perfectly the total number of examples we found with the full dataset. We estimate that by doubling the size of our auxiliary dataset, we might be able to find an additional 20% of the data that the model remembered. However, this assumes that any new data we add to our auxiliary dataset would be similar to the data we've already collected. We looked at the amount of data we found as a result of adding each of the 4 datasets that make up our auxiliary dataset. As expected, the largest dataset, DOLMA, contained the most examples. But we were surprised to find that the size of the dataset didn't completely determine the number of examples we found. For example, the 1 terabyte refined web dataset found the least amount of data, and almost all the data found by the 2 terabytes Red Pajama dataset was already covered by one of the other datasets. We think this is because the distribution of each of these datasets is different from the dataset that GPT 3.5 Turbo was trained on. We also tried to estimate the true rate of memorization by manually searching the entire internet for 494 generations of data. We found nearly twice as many examples in our manual search than in our auxiliary dataset. This suggests that adding more datasets would improve our ability to find memorized data. Section Summary. The section discusses the estimation of ChatGPT's memorization rate and the limitations of the analysis. It is suggested that ChatGPT likely memorizes at least 1.5 million unique 50-token sequences, but this estimate may be poor due to the limited number of examples extracted. Comparisons with other models indicate that ChatGPT emits unique memorized strings at a much higher rate. Increasing the size of the auxiliary dataset leads to the discovery of more memorized output. Additionally, manual search analysis on the entire internet confirms that ChatGPT memorizes nearly twice as many model outputs compared to the auxiliary dataset. Section. An end-to-end high-precision attack. We've been focusing on how language models memorize data, using our ability to directly access the model's training dataset to identify memorized outputs. However, without a surefire method to determine if a model's output is a training example, we can't label this as an extraction attack. We're now going to demonstrate that existing methods can effectively differentiate between memorized training data and other generated data. We'll use a technique known as the membership inference attack, which is highly accurate at separating memorized training data from other data that wasn't part of the training dataset. We'll assign a score to each example based on their likelihood ratio perplexity over text perplexity. The numerator represents the perplexity of the text as determined by the model that generated the text, while the denominator corresponds to the entropy of the sequence under text compression. This ratio has proven effective at predicting memorization in previous studies, and we found it to be highly accurate in our setting as well. We've also examined how changing the membership inference threshold impacts the precision of our attack. At the lowest threshold, the attack precision is above 30% when evaluated by a manual internet search, or still 15% when evaluated by verbatim membership in a UXDATASET. By increasing the threshold, precision remains relatively constant until it reaches 1.5, at which point it begins to significantly decay. This suggests that we can not only extract training data, but we can also accurately identify when data is memorized and when it is not. However, there's still room for improvement in the precision of this attack. In our attack, we extract training data by causing ChatGPT to diverge. However, this method isn't applicable to other models, and therefore isn't a reliable way to test for memorization in general. If we had access to examples from the training dataset, we could check for discoverable memorization, which could allow us to estimate the amount of memorization. We found a workaround for not having access to the training set. We do know part of ChatGPT's training set because we just extracted it. So, we can take these samples that we know are in the model's training set, split them into a prefix and suffix, and then measure discoverable memorization of these. When we prompt the model in this way, GPT 3.5 Turbo completes the corresponding 50-token suffix in just 3.5% of cases. In a further 4% of cases, we approximately recover the suffix. It has a Levenshtein distance less than 0.1, which allows up to 5 tokens of difference. Over 90% of the time, the model fails to emit the memorized output that we know to be memorized. This suggests that it will be difficult to evaluate this model's privacy without additional access to both the model and the unaligned foundation model from which it was derived. The GPT 3.5 Turbo Instruct model is closer to a base language model because it is not conversational. As a result, we can test for discoverable memorization in the instruction-tuned model, and hope to get a better estimate of the true rate of memorization of the base GPT 3.5 model. We repeated the experiment above and found that the Instruct model successfully completes the suffix in 75% of cases, and in 84% of cases the output is within 5 words of the true suffix from the training data. Section Summary. the authors conducted an evaluation to measure the memorization capabilities of language models and found that existing techniques can accurately distinguish between memorized training data and generated data. By using a likelihood ratio based on perplexity and entropy, they achieved high precision in predicting memorization. However, the attack method they used is not generalizable to other models, and discoverable memorization in ChatGPT was found to be low. To evaluate the privacy of the model, additional access to both the model and the unaligned foundation model is necessary. Section: Consequences. Let's delve into the implications of our findings. We've come to 3 intriguing conclusions. Firstly, the 2 models we examined, GPT 3.5 Turbo and GPT 3.5 Turbo Instruct, seem to remember the same samples, even though they were likely fine-tuned on different datasets. This implies that the data they remember comes from the initial pre-training data, not the fine-tuning data. Secondly, it appears that data memorized during pre-training persists, regardless of the different fine-tuning setups. Recent studies have shown that while models may eventually forget memorized training data, this process can take several cycles. Given that pre-training usually lasts much longer than fine-tuning, we believe this is why there's been minimal forgetting in this case. Thirdly, our previous findings suggested that auditing the privacy of black box RLHF-aligned chat models would be extremely challenging. However, it might not have been as difficult to audit the original base model from which GPT 3.5 Turbo and GPT 3.5 Turbo Instruct were derived. Unfortunately, since this base model wasn't made public, it would be hard for others to externally assess its security. Now, let's discuss why ChatGPT is so susceptible to data extraction attacks. We have a few theories, and we encourage future research to explore these further. One reason could be that ChatGPT is pre-trained for many cycles. To support its high-speed inference and large-scale service, models are often overtrained on more data than what would be optimal for training computation. This maximizes utility at a fixed inference cost. For instance, the 7 billion parameter Llama 2 model trained on 2 trillion tokens performs better than the 13 billion parameter model trained on just 1 trillion tokens. Given the limited amount of high-quality data on the web, training on such a large number of tokens requires many cycles over the same data. We suspect that ChatGPT may have been pre-trained for many cycles, which previous work has shown can significantly increase memorization. Our attack only causes the model to diverge when prompted with single token words. We don't have a clear explanation for this, but the effect is significant and easily repeatable. After repeating a token 250 times, the likelihood of repeating the token again rapidly drops from 90% to below 0.1%. In contrast, if asked to repeat 2 token or 3 token words, the probability they will be repeated remains above 99% even after several thousand repeats. During pre-training, modern language models are trained with packing. Multiple documents are combined to form a single training example, with a special token used to mark the document boundary. This teaches the language model to reset when it sees this special token, and ignore all previous tokens when predicting the next one. We suspect that our attack works because it creates an effect similar to this special token. To illustrate this, we studied Llama 7B, a model that also diverges after repeating a single token many times. We prompted Llama 7B with a single token repeated many times, and measured the cosine similarity between the last layer, attention query, of each token in the prompt with the beginning of sequence, boss, token, Llama's equivalent of OpenAI's special token. We found that when repeating a single token many times, the last layer attention query for those tokens rapidly approaches the attention query vector of the boss token. This may cause the reset behavior we observe. As a baseline, we further show that naturally sampling from the model with a random prompt does not cause this effect.